All right. So, I feel like we haven't taken notes in a while. The last thing, no, we did actually. The last thing we talked about was shielding, correct?
Yeah.
Okay. So, let's just review shielding really quick. Shielding is the electron repulsion between inner electrons. Sometimes inner electrons are called kernel or core electrons. So if we take, we'll just use chlorine as an example. 1s2, 2s2, 2p6, 3s2, 3p5. There's chlorine. So here's your valence electrons. There's 7 of them, right? These here shield the valence from that positive nucleus. So again, you kind of think of it as like an actual shield because there's electron repulsion. All right. So the more inner electrons or core. So sometimes these are called core electrons. Sometimes they're called kernel, like inside a popcorn kernel. Like they're inside the inner electrons. They will repel the outer, which are the valence electrons. So it makes sense. There's lots of things that hopefully start to make sense this year. As you move down the groups, there's more and more energy levels, so there's more and more shielding, which is why these atoms get bigger and bigger and bigger, and why it's easier to remove. Ionization energy is lower, easier to remove from the really big atoms. Okay, like francium. It's like very simple to take an electron from francium compared to lithium. Okay, francium's so big with lots of shielding. So I just wanted to review that concept with you. All right, so that's shielding. All right, so now your homework, I want to explain because I'm probably just going to go right to the bell here. Look at that sheet I gave you. I forget what the title says. It says PES data or something like that. What's it say in the top? Photoelectron spectroscopy. Now, if you look up here, let me pull this down. Okay, so this is just really so it doesn't glare so bad here on that thing. I want you to go to my website. This is for homework. Okay, go to Mr. McCoy's website. You know, this cool website here. And then you go all the way down where it says there's a ton of stuff here. But AP Chem, maybe I should make that bigger or whatever. But AP Chem down here, links and videos. I want you to click on PES tutorial video. All right, when you click on that PES tutorial video, that's going to pop up, and I want you to play it. Obviously, you can use your phone, whatever you need to do. You got to watch that, and then, well, while you watch it, you're filling in. I don't know if you guys can see here, but there's blanks that match the blanks you have. All right, this is cool. I wish I had more stuff like this, but I just don't. But I have it for this, so we're going to use it. So this is a great way to learn what the heck is PES. I'm going to introduce it maybe today if I have time, but I really want you to watch it, fill in the sheet there, the packet I gave you, so you kind of know what it is already before you get here tomorrow, and then we'll go through it, I'll go over it, we'll take notes on it. I have another sheet that I'll be giving you for homework. There isn't anything in our book about this. This is pretty new stuff as far as like actual real life application. So basic explanation I can give you really quick is if you look at that sheet, there's peaks on it. Peaks represent electrons in orbitals. That's what that means. So this PES data is a way you can analyze a sample and you can actually figure out the electron configuration just based on what this graph shows. All right. So we'll talk more about that tomorrow, but I didn't want to forget. That's what I want you to do for homework. It shouldn't take you that long. I have no idea how long the video is. Let's find out. Oh, 18 minutes. Well, have fun with that. So I thought it was shorter. So anyways, listen, I'm not, I wasn't born yesterday. What did I say in forensics? I didn't just fall off the turnip truck. So I realized you can skip ahead. You do whatever you want with the video. Here's what I need you to do. Complete the worksheet and be able to explain what the heck this is. All right? So I may pair you up tomorrow, compare your answers, talk about it, and then I may have some random groups or people actually explain to the class what it is. All right, so we'll see. So just make sure you know what it is and fill in the packet. All right? I didn't realize it was so long, but I guess that's life. All right. Okay, so now we're going to move on here. we're going to learn about Coulombs law, the photoelectric effect, but first let's talk about this, the Bohr model of the atom. What do you notice about the distance between the energy levels on the Bohr model? They're the same, okay? And we say first level, second level, third, fourth, but another labeling method is the alphabet. They use K, L, M, and N. And they started with K because they weren't sure if there were other levels within K that they just didn't know about. You know, so A through whatever. I just have to say the whole alphabet. But anyways, I thought that was kind of interesting or pretty smart of them. But anyways, this is how everybody kind of learns atoms and electron levels when they're little, and then even in Regents Chem. I still use it with you guys, but now you really need to know it doesn't actually look that way. All right? So here's what I want you to write in your notes. Just sketch what the Bohr model looks like, and then write, it isn't completely correct. The distance between the energy levels is not equal. So you can paraphrase that however you want. But the goal today is to understand how Coulombs law factors in here. We're going to learn about this thing called photoelectric effect. Physics people, you heard that? Heard that? No, maybe? All right. We're gonna talk about a couple formulas we're going to get into. Not yet, but I need to bring them up to explain the photoelectric effect and energy levels. All right, so we're just going to be taking notes the rest of the period, kind of learning the concepts here before we can apply it. Physics people, you've heard of Coulombs law. I brought that up in here before, haven't I? Sort of, maybe? Yes, last week I thought. All right, so that's that. Now, what's next? Okay, this is, I want you to get this down. All right, is that big enough? No? Is that better? Copy that down. That's not better? Really? It's not that small. Well, if you can't see it, move up. So this is a more accurate representation of the energy levels. You have your nucleus down here. You have your first energy level, which is very close to the nucleus. And then there's a significant gap between 1 and 2. So the distance between energy level 1 and energy level 2 is pretty big. Then the distance between 2 and 3, 3 and 4, 5 and 4 and 5, 5 and 6, it gets progressively smaller. And then between 6 and 7, they're almost right on top of each other. And this is going to help us understand the transition metals in this thing called band theory, which we learned a little bit about. It's a little confusing to me too, I'll be honest. But explains why metals conduct electricity so well. So we'll talk about that down the road. But the fact that these energy levels here, 5, 6, 7, are pretty close together. So especially the elements in period 5, 6, and 7, it makes a little sense. We'll talk about it. But I do want you to try and mimic the distance here the best you can. And if you need to write notes to yourself, just write, there's a big difference, big gap between 1 and 2, and then the gaps start to shrink. And now what these arrows are representing are the transitions of electrons. So when electrons gain energy, so they start in their ground state, wherever that is. When they gain energy, they jump up to higher energy levels. And when they fall back down, they lose that energy in the form of what? Light. Well, remember, light is a whole spectrum. You have ultraviolet light, okay, to, gamma rays, cosmic rays are the smallest, all the way up to radio wave, microwaves. Radio waves are enormous wavelengths. So light is all types of different wavelengths of light. It isn't just what we see. All right, so I like to show this because if you have an electron that is transitioning from the 7th, 6th, 5th, 4th, 3rd, or 2nd down to the first energy level, that's called the Lyman series. We can't see that with our eyes. That's not visible light. Visible light is the Balmer series. When we do that lab in Regents Chem where you see the spectra and you use your spectroscopes, okay, or when you look out and you see a rainbow, that's the Balmer series. We can see that. That's transitions to the second level. Paschen series transition back to the third. Brackets transition to the fourth. And you would think I would have this memorized or written down, but I don't think I do. I forget. So like one of these series is ultraviolet light. Another one is X-rays. Maybe I did write it down. Let me look real quick here. Yeah, I guess not. I thought we did. I mean, I can look it up quick, but I'll do that some other time so we can move on. But the Lyman series, Paschen, and bracket, it's different wavelengths of light. Different wavelengths of light. All right? So, I think it makes sense if I'm correct here. No, never mind. I'm being recorded, so I don't want to quote myself and be wrong. So I'll look it up. I know there's X-rays, ultraviolet involved with the different series, but what I'm really trying to show you is this is more accurate than this. Okay, it's not all the same distance, and a lot has to do with the energy of the electrons on these levels. And one thing I do want to make sure we understand is the energy is quantized or quantized. What that means is every electron on the first energy level has a specific amount of energy. Every electron on the second has a specific amount of energy. Same thing with third, fourth, fifth. You can't, if you're an electron, you can't live in between. You either have all of that energy or none of that energy, and at that point you have an energy at the first or third. So it's these bundles of energy called quantum, that dictate where electrons are. There isn't like fractions of these energies. You're either all on this level or you're all on this level. There's no in between. Okay? That's what quantized means or quantized means. So when you give electrons energy with heat or electrons or heat or electricity and they jump up, if they're gaining a specific amount of energy. All right? And that's where these equations are going to come into play. All right? Does everybody have that down? Everybody good? Taylor, can you see what's going on here?
Yeah.
A little bit. All right. Somebody can see. All right. Here's another thing I wanted to show you. Here, let me zoom in a little bit here. I'm going to forget I zoomed in and then later something's going to be massive. But, all right, so this is just what I was getting at earlier. This you need to have a rough understanding of. So again, you don't need to memorize it because if you know you start at hydrogen and we just fill, we go right, left, right, just imagine we're wrapping around the back, right? So we go right, and then we go left, and then we go right. So we're wrapping around that thing as we work our way down, and it goes from low energy hydrogen all the way up to OG 118. So if you know the blocks and you know the order, you don't need to memorize this. But you do need to know this. You need to be able to explain it and understand why the 4s fills before the 3d. It's lower in energy. The 5s fills below the 4d. But as you get higher and higher, and I know I'm saying a lot, but this is really important stuff. I hope you're paying attention for a Monday here. Notice the big gap here. That corresponds to the last picture we just looked at. As you get higher and higher, they get smushed together. There is a difference, but it's really small. The more electrons you have, what happens is the orbitals get so close together, they kind of mush together, and it's called a band. I'm saying that because it's going to help us down the road. You don't need to know that term right now, but they get so mushed together, there's so many electrons, that when we're down in here, in the transition metals, again, it's called band theory, it's almost like the orbitals are so close and start to overlap, the electrons kind of get confused where to go. And we'll talk about that. But down here, it's a noticeable difference. All right, and I have a Khan Academy video. We're going to watch bits and pieces of it, and he does a good job. He or she, I forget who it is, just describing why. Why is there such a big gap here but not up there? And there's a little physics involved, so I think it's good to watch. All right. So we're going to watch that right now because I've never really stressed this much as I am right now with you guys, but I think it's really important. I should have been doing it for years to really explain why the Bohr model is wrong. All right. And a lot of it has to do with the energy associated with these levels, and that's what this video is going to show. All right. So what are you writing in your notes? Make sure you have that sketched and you understand that's wrong. This is down and this is correct. And again, this corresponds to that. And it should make a little sense at right now at this point. All right. Now, let me play some of this here. Oops, sorry. See, I already watched this a little bit here. All right, here we go.
In the Bohr model of the hydrogen atom, we have one proton.
I almost started talking like I was talking to my daughter. Wow. Okay. Coulomb's law. Copy that down. Coulomb's law. And I want you to draw this little picture right here. What's going on? Oh, we'll get back. Oh, you need to see that. Okay. Coulomb. C-O-U-L-O-M-B apostrophe S law. I'll explain it. Just write that title down and then draw that picture with the equation. This F sub 12, F sub 21, it just means 1 and 2, or 2 and 1. You don't need the 1, just write F, okay? F equals K times Q1 times Q2 over R2. I forgot, I need to explain this a little bit first before we watch the video, because this explains the distance between the energy levels and the nucleus, because the nucleus is attracted to the electrons. Basically, Coulomb's law is a law that helps explain how positive and negative charges are attracted to each other, which is called an electrostatic force. You've heard me say that before, I hope. That rings a bell, sort of-ish. And again, you don't need to make, this doesn't need to be like, an artist's drawing here. Just sketch, you have one particle with a positive charge, one particle with another positive, they are going to repel. And then if you have a positive negative, they're going to attract. That's all that's shown. But the distance between them obviously plays a role. Think about magnets. If they're really far apart, they're not going to really feel the effect. But if they're really close together, they will. So the radius of the particle, the radius between the particles, right, the center of both particles, that plays a role in how well or how much they're attracted or repelled. Again, you take two particles that are same charge, they will repel, but it depends on how close they are together. All right, so this is just kind of a picture example of what Coulomb's law is. And Coulomb physics people, what's a Coulomb? What's Coulomb the unit used for? Charge. It's like the amount of positive and negative charge something has. It's called Coulomb because it's named after Coulomb's law. All right. So Coulomb's law states that like charges repel, unlike charges attract. But the more complete form determines the strength of the Coulombic force. Here's what you're going to write down. Coulomb's law shows how strong the pull or push is between 2 points of charge. That's what Coulomb's law basically is. It shows how strong the pull or push is between 2 points of charge. So two particles that have charge, it can tell us the strength of that pull, whether it's a pull or a push force. Okay. Friction is an example of Coulombic force. The normal force. What's the normal force? Physics people? It cancels out gravity, doesn't it?
Yeah.
Is the normal force like pushing up?
It cancels gravity.
Yeah.
It's on a horizontal.
Right. So like right now, gravity's pulling me down, but the normal force is keeping me upright as well. Yeah. So if you take, I like that stuff. I don't know. Did you guys like physics?
Yeah, I love physics.
Yeah. Yeah. You told me. Yeah. I like physics. When I got into college, chemistry majors had to take. We had to take physics major classes for the first year or year and a half, and I struggled. I didn't do well as far as grades, but I kind of liked it. It was just hard. Anyways, back to this. The part that we really care about is the proton and electron in an atom, right? So make sure you put that down. So the Coulomb's law and Coulomb's force of attraction here that we are focusing on is the positive nucleus and the negative electron, right? So that attraction kind of dictates the size of the atom, right? And the energy levels, the distance between energy levels. So that's why I'm bringing it up. All right? But let me explain a little bit about the symbols here. F stands for force, right? So you're going to want to write this down. F stands for force. K is a constant. Now, I'm not going to actually have you use this equation. You don't have to do calculations with this. It's just understanding what Coulomb's law is and then why this equation is relevant. You're not going to actually do calculations. So K is a constant, and we don't need the numbers right here, but you don't really need to know it. Q1 and Q2 are the two charges. And the unit on that is coulombs, or capital C. So coulombs, the unit is C, capital C. And then R is the distance in meters. Now notice, and I'm going to click on this here, the R is squared, right? So that's going to play a big role in the distance between the energy levels. That square kind of changes everything, all right? So again, this might seem kind of like complex, but really all it is what's that force between the positive and negative charges? And I just want to read this to you. I thought this was interesting here. Oh, and you do need to write this down too. The electric force of one charge on another depends on the magnitude of charge and the square of the distance between them. So I want you to write this down. The magnitude of the charge plays a big role. What does that mean, the magnitude of the charge? What's the word magnitude mean? Yeah. So if you have a positive 1 and a negative 1, they will not be as attracted as a positive 2 and a negative 2. That's what Coulomb's telling us. The magnitude of the charge is a big factor in how well they attract or repel. All right? So the more protons in the nucleus, that's a larger magnitude of positive charge, right? But the square of the distance, the r squared, that also plays a role. Okay, that also plays a role. So where we're headed with this is if you have, I'm getting a little bit ahead of myself here, but if you have a set distance between, so let's say you have two particles here and two particles here. Let's say these two are this big, but these two are that big. Which two are closer? The bottom two, right? So the bigger the charge, the bigger the particle, and the more magnitude, the stronger this force is going to be. In other words, the distance between here and here, let's say is r, let's say that's the same, okay? But because this particle and this one are bigger, the distance of their charge interacting is actually smaller. And if this one is +1 and -1, and this one is +2, -2, these two are going to experience a ridiculously strong force compared to them. So I'm getting a little ahead of myself. You might be confused. Let me kind of recap to make sure you're getting what you're supposed to. What is Coulomb's law? The equation's written down. You can actually calculate the force of attraction between two charged particles. That's what this law tells us. Or the force repelling them, if they're the same. Okay? Coulombs is a unit. That tells you how much charge is on a particle. All right? All we're using it for really is the nucleus and the electrons. Later, we're going to use it for ionic compounds, cations and anions. That's what this is all about. All right? Let me just read this. You don't have to write this down. But the magnitude is a big deal. All right. The electric force pushing two protons in a nucleus apart is enormous compared to the gravitational force, about 10 to the 41st times larger. I don't know if you can see all those zeros, but that's insane. So the force pushing protons apart is 10 to the 41 times greater than the gravitational force. Coulomb's law inside the nucleus of an atom is what led scientists to postulate the strong force, which holds the nucleus together, which is even stronger than the Coulombic force at short distance. So in other words, this equation, when this r becomes extremely small, there's another force called the strong force that takes over, and that is way stronger than the protons repelling. So just the factor of 10 to the 41st, and then the strong force is stronger than that, I mean, it has to be, right? Think about it. If our nuclei that holding us together wasn't strong, I mean, everybody would just disintegrate, right? So, I don't know. I find that stuff interesting. It's kind of cool. So the very short range of the strong nuclear force is what makes it so difficult to derive energy from fusion. Because we're messing with that force. To try and do fusion on Earth, we can't really do it. Not very well, not complete, like the sun. So the pushing part of protons creates what's known as the Coulombic barrier. So anyways, it is important you understand what that is. What is the Coulomb's force? Coulomb's law, Coulombic interactions. There is one more word I want you to write down. Coulombic force and electrostatic interaction is the same thing in chemistry. It is in physics too, basically, but Coulombic force and electrostatic force, both of them imply positive, negative attraction or positive, positive, negative, negative repulsion, whatever. Okay, so those are the same thing. You see that? It means this. You see that? It means this. And again, why am I bringing this up? Because you need to know what this means before we get into the video, which I'm not going to have time for today. So that took a little bit longer, but maybe I talked a little too much about it, but I really think it's important to understand. So we're basically done. Bell's going to ring. Do that PES worksheet. We will get to that tomorrow because we have double period. Please look at your lab. If you have questions, I'll address it in class with everybody. So look through all those questions if there's something you think you're going to need help with. When did we say that's due? Let me write that down. Friday. What? Due Friday. What's the date on Friday? 20.
26.
He's just yelling out numbers.
26 direct.
Okay. 26. All right. So we're just going to write econfig lab. And your PES due tomorrow. Due Tuesday. PES worksheet.
How do you know what day it is?
Next Wednesday.